everyone. So I'm afraid the sound on this video might sound a little bit weird because my microphone broke. Hopefully I'll have the microphone ready and working for the next video, but till then, well, it's not so bad, and this is going to be a pretty short video anyway. So the topic here is volume. And I like to do volume as its own special topic before I get to the next topic, which is density. And of course, volume is part of density, and hence why I want to do it as its own separate pre-lecture. So what's volume all about? Let's start by defining volume. Volume is simply the amount of space occupied by matter. Now, a big issue for us are the units used to measure volume. And what are they? Well, there are a quite large variety of units used to measure volume. Now, from a scientific perspective, whoops, let's try that again, the SI unit that we use for volume, we already worked out in a previous lecture, and that is the cubic meter. Now, it turns out all cubic length units are, in fact, volume units. So I'm just going to write that here, cubic length. Any unit that is a length cubed is a volume unit. So that would include things like, say, cubic centimeters, or cubic feet, or cubic kilometers, and we could keep on going and going and going with this. But they're all volume units, even though the technical SI unit is the cubic meter. Well, there's another system, a very important system of volume units that we scientists like to use, and that is the liter. The liter, which is abbreviated capital L for liter. So as it turns out, even though it's not the SI unit, the liter is an important metric volume unit. So I'll write that here, important metric unit for volume. Now, because it's a metric unit, we can use our metric prefixes to make it bigger or smaller, and therefore it is not unusual to have things like milliliters, or perhaps picoliters, or deciliters, etc., etc. Now, a very important conversion relationship between the cubic length system of volume units and the liter system of volume units is one that you learned before in Chem 10, and I'm going to remind you of it now, and that is this, that 1 cubic centimeter is identical to 1 milliliter. Really important conversion relationship, allowing you to get from one volume system to the other, and it's so important, I'm not just going to star it, I'm going to highlight it in bright yellow. You should probably do the same. Now, what about other volume units? Of course, there are other units. Well, the other units out there for volume would be typically units that you use in your everyday life, but we're going to use very rarely in our chemistry course. And they might include units such as, say, gallons, or quarts, or pints. And some of these units show up on the conversion relationship sheet that you received with your earlier lecture notes on the topic of units. So you may notice that these are there along with appropriate conversion relationships. But again, they're everyday units, not as important. I'm not going to be focusing so heavily on them at all. Now, let's talk about how we measure volume. Turns out if we want to measure the volume of either a liquid or a solution, we can do so directly by using the appropriate type of lab glassware. So, for example, the most common type of lab glassware used to measure volume, liquid volume, solution volume, is of course the good old graduated cylinder, which is provided to every student in a real live in-person lab. But unfortunately, we don't have that right now. But there are other items that are used to measure liquid solution volume directly, and you may have heard of some of these. For example, a volumetric flask is a very useful device to measure liquid and solution volume, and a volumetric pipette. And both of these you will meet in some of our labs later this particular semester. Okay, now whereas we can measure these volumes of liquids and solutions directly, it's a little bit different for solids. Turns out that the volumes of solids must be determined indirectly. And one of the more popular ways of doing this is to use the technique of water displacement. So let's see if you remember how this works. If we have some water in a graduated cylinder, so let's put some water in here. And of course the water will have a meniscus. There's the meniscus. We can record the volume from the bottom of the meniscus, we might remember here, as our initial volume by using the scale on the graduated cylinder. Now let's suppose we have a solid. Here's our solid. And we would like to know the volume of this solid, where what we would do is simply place the solid very carefully into the water. And of course, what's going to happen now is that the water level rises. The water gets displaced by the volume of the added solid. So let's put our meniscus back in here. Let's put our little purple solid in here. There we go. And of course, now we can read the new volume, or the final volume, which I'm going to designate VF. V initial, V final is what we have here. And again, we're reading these values directly from the scale of the graduated cylinder. And very simply, if we want to know the volume of the solid placed in the water, it is just the final volume minus the initial volume. Now, there's some caveats to whether or not this technique is going to work. So for starters, for this technique to work, we need for the solid to sink in the water and not float on the water. And what determines whether the solid sinks or floats is, drum roll please, the densities of these two substances. The density of the solid needs to be higher than the density of the water. So let's note that the solid must sink. In other words, the density of the solid must be greater than the density of water if we're going to use this technique. Something else that's important about this technique, and that is that the solid cannot either dissolve in the water or chemically react with the water. So the solid must not react with or dissolve in the water. So what would you do if you had a solid that was going to dissolve in water? Let's say sodium chloride. You couldn't use this technique for sodium chloride because sodium chloride dissolves in water. Well, the good news is this technique works with other liquids. So instead of putting water in the graduated cylinder, we could replace it with a liquid that the salt does not dissolve in, excuse me, but will still get displaced the same way. Oh boy, excuse me there. So let's write this as our last note here, that liquids other than water can be used, or just say other liquids can be used. Okay. Now, this technique of water displacement, as long as the caveats are met, will work to help us determine the volume of any solid. However, if we are lucky enough to have a solid that has a regular geometric shape, well, another way to get their volume is to simply measure their dimensions and then plug those measurements into an appropriate volume formula. So, for example, if we wanted to get the volume of, say, a cube, of course, has all equal length sides. Well, the volume of a cube is given by length cube. Now, if we have the volume of a box, the technical name for a box, if you're taking a math class, is a rectangular prism. How many of you remembered that? So rectangular prism is what I'm going to write here. Well, in this case, the length is different from the width is different from the height, and so we would write this out as length times width times height is how we would calculate the volume of a rectangular prism. And I'm just going to note here that another way to say that is, oh, it's like a box shape. Or perhaps we could get the volume of a cylinder, such as a coin. And we would do that using the measured dimensions and the formula pi r squared h. R squared represents the radius of the base of the cylinder, which is a circle, and h represents the height or length of the cylinder. Let's add one more for good measure. These are the most common ones, and that last one here would be the volume of a sphere, which is given by the formula 4/3 pi r cubed. And that's a terrible 4/3. I'm going to rewrite that so you can more clearly see it. 4/3 pi r cubed. Okay. If you think about it, volume is three-dimensional compared to area, which is two-dimensional. And so one thing we should note that the way we get from an area to a volume is that area needs to be multiplied by the third dimension, which would be thickness. So we could think of in general that the volume of anything is equal to the area times its height. Height or its thickness. Or perhaps its depth. So I'm just going to put this as an aside. As a general rule, volume equals area times height. So let's think about the prism, the box. Well, length times width is area. So it's area times h, which is height, area times height. Or if we think about a cylinder, the base of the cylinder is a circle over here. What's the area of a circle? Pi r squared. So we have pi r squared, which is area times height. So again, volume is just area times height, something to keep in the back of your mind, very useful. Now, let's take a look at ICE problem number 8, which is a problem involving volume calculation and volume unit conversion. And the problem simply states, a spherical platinum nanoparticle has a diameter of 23.4 nanometers. It's a teeny tiny sphere is what we're dealing with of platinum. Calculate the volume of this nanoparticle in A, cubic nanometers, and B, liters. So the information we have about this platinum nanoparticle is twofold, and I'm going to highlight two things. All right, first, the measurement, which is a diameter. And the second is the very symmetric shape of the nanoparticle, which is a sphere. So it's useful to know that the particle is in a spherical shape because we have the volume formula for a sphere, 4/3 pi r cubed. But in that formula, 4/3 pi r cubed, we don't want diameter, we want r, which is radius. And so the first question is, what is the relationship between radius and diameter? Well, as it turns out, radius is equal to half the diameter. So radius equals 1/2 the diameter, which in this case would be 1/2 of 23.4, or working this out, it's 11.7 nanometers. Is the radius of our sphere. Well, now that we have the radius of our sphere, we can do part A, which is to get the volume in cubic nanometers. And to do that, we're simply going to plug and chug with the volume formula. And that is that the volume of our spherical particle is equal to 4/3 pi r cubed. Now, r we just figured out is 11.7 nanometers. And we've got to cube this. And so all you've got to do at this point is pull out your calculators and plug and chug it out. Now, this is where it becomes really important to know the functions on your calculator. Where's the cubed function? Where's the cube root function, the square function, the square root function, and know how to plug those keys in the correct order to get the right answer. That's not something I can help you with during this lecture, obviously, but if you're having trouble with your calculator and getting the right answer, please bring this up to me during office hours. That's the best time I can help you with this. The best way you know that you're not working your calculator correctly is if your result when you plug and chug is different from my result. So always plug and chug these answers out yourself to make sure that you know what you're doing. So I did plug and chug this out, and I ended up getting that the volume of our tiny nanoparticle as 6.71 times 10 to the 3. And what units do we get? Well, we have nanometers being cubed, and so our units are cubic nanometers. Okay, that's the easy part here, just plugging and chugging in the formula. Part B, however, is a conversion problem. We want to also calculate this volume in liters. And so this is a conversion problem where we start with 6.71 times 10 to the 3 cubic nanometers, and we're going to have to go through step by step and convert this to liters. So as we saw in our previous lecture, when we're doing conversions, it's best to start by mapping the problem. So how are we going to map this problem? Well, we have cubic nanometers. What do you think we should go for next? Well, it turns out the most sensible unit to go for next would actually be the cubic centimeter. They're both part of the cubic length system. And why would we want cubic centimeters? Well, here's where we're going to remember that a cubic centimeter is identical to a milliliter. So it's a quick hop from cubic centimeters to milliliters. And then once we have milliliters, we can take it all the way home with what we're really after, which is liters. And this would be our problem map for this particular unit conversion. So for each of those arrows, we're going to need a conversion relationship. So what are we going to use? Well, let's start with the easiest one, cubic centimeters to milliliters, where we know that 1 cubic centimeter is exactly the same as 1 milliliter. So there's the conversion relationship we need. We can also take an easy look and get the conversion relationship for the last step, milliliters to liters. We know that 1 big unit equals many little units, and liters definitely are the big unit. So 1 big liter equals 10 to the 3 milliliters. So as it turns out, the only difficult, I'm going to put difficult in quotations here, conversion relationship to obtain is the conversion relationship for the first step, which is cubic nanometers to cubic centimeters. So how do we get this relationship? Well, the place we begin is with the regular relationship between non-cubed nanometers and non-cubed centimeters. So what's the relationship between a centimeter and a nanometer? Well, I would start by remembering that we put the big unit first, and a centimeter is definitely bigger than a nanometer. So 1 big centimeter equals how many teeny tiny nanometers? Well, as it turns out, it is 10 to the 7 teeny tiny nanometers. Now, that's the relationship between centimeters and nanometers, but we want the relationship between cubic centimeters and cubic nanometers. How do we get it? Well, we take this expression and we cube it. So if I cube all the terms in this expression from left to right, well, 1 cubed is 1. Centimeters cubed are now cubic centimeters. Next, we get to the 10 to the 7. Well, what happens when we cube 10 to the 7? Well, we have to multiply 7 by 3, and we end up with 10 to the 21. And now our nanometers get cubed, and we now have cubic nanometers. So there's the conversion relationship we need for the first step. Now at this point, it's all just classic dimensional analysis. So here we go, 6.71 times 10 to the 3 cubic nanometers times, well, let's start with our first relationship. We want to get rid of the cubic nanometers, so we're going to put 10 to the 21 cubic nanometers in the denominator, 1 cubic centimeter in the numerator. What happens? Goodbye, cubic nanometers. In our next step, we want to get milliliters, so we know that there's 1 milliliter for every 1 cubic centimeter. What happens now? Goodbye, cubic centimeters. And in our last step, we're going for the liters, 1 liter for every 10 to the 3 milliliters. Time to say goodbye to the milliliters. After all this, what's left? Well, what's left is the unit we were after, which is the liter. Let's also notice that this 10 to the 3 in my original measurement is going to cancel with this 10 to the 3 down here. So goodbye 10 to the 3s. And so what do we get in the end? Well, in the end, we end up with 6.71 times 10 to the negative 21 liters as the volume of our nanoparticle in liters. And I'm just going to put little boxes around the two volumes that we calculated in this problem. There we go. Okay, so our short little lecture is done. Like I said, we're going to keep it short. Just wanted to have a refresher on the topic of volume before we jump into the bigger and more complex topic of density, which is in our next lecture. So take care, everyone, and I'll be talking to you very soon. Bye now.